Hello, and welcome to part 1 on my video project about non-Newtonian fluids. So, today we're going to look at a common substance known as oobleck, which is just a mixture of water and cornstarch. So, like water, oobleck, when we pour it, will flow very similarly to water. It's a little bit on the thick side, but still, it flows just like any other liquid that we're used to in everyday life. However, when we subject oobleck to an impulse or a large force over a short period of time, we notice some interesting things happen. So, I'll pour the oobleck in this bowl here, and we can take this fork, and when we move it slowly, this is just like any other liquid. Just like water, I can drag the fork through, no problem. But when I try and move the fork quickly, there's a lot of resistance, which is something interesting. And even more dramatically, when I try and stab this, the surface acts almost like a solid. It doesn't splash at all. To demonstrate this really effectively, I'm now going to hit the oobleck. And we can see, even as I'm hitting it really hard, the surface basically stays solid. And I only have a little bit of oobleck on my hand. And of course, just to prove to you that there's no magic here, if I go ahead and slowly dip my hand in, yes, my hand will become covered in oobleck. So, this is part 1 of the series, which is just giving you an idea of what we can actually see when we play with this stuff, and I encourage you to go ahead and get some cornstarch and some water. You mix roughly 2 parts cornstarch with 1 part water, and that's how you make your oobleck, and you can play with it and do all sorts of fun things. In order to understand what's going on here, the physics and the science of this, please see part 2 of the video that goes through some of the theory of non-Newtonian fluids. Thank you and have a good day.
No video discussing the physics of anything would be complete without a few hard facts, an equation or two, and some graphs. So here we'll explore the physics of non-Newtonian fluids in a more rigorous way than we did in our earlier demonstration. First, we may delineate matter into 4 common states that we're familiar with, excluding a few exotic categories. The 4 states we usually refer to are solids, liquids, gases, and plasmas. Solids usually have a highly organized or crystalline structure, and as energy is added, corresponding to an increase in temperature, a solid may become a liquid, which will conform to fill whatever container we place it in. After adding additional energy, this can lead to vapor or gas forms, and taken to the extreme will cause ionization, where electrons are actually stripped off of the material's nuclei. A common example of this process that we know of would be heating ice, which will melt to form water, and eventually boil to become steam, and even a plasma if extreme conditions are applied. On the right is merely a diagram depicting these processes with the correct terminology of each process when converting from one form of matter to the other. Now that we have an idea of the different states of matter, we can specifically focus on fluids. Newtonian fluids, such as water, are things that we're quite familiar with. They may be described in terms of their viscosity, or in simple terms, how much work must be done to deform them. In the case of water, we may easily pour it into a glass. This is contrasted by higher viscosity materials such as honey, which flow more slowly at similar temperatures. The viscosity of these fluids is primarily only a function of the temperature. This means if we apply more force, or shear stress, the fluid will flow more rapidly. This is the essence of Newton's viscosity law, which states that the velocity gradient perpendicular to a surface as a result of a shear stress is proportional to the applied stress. This is depicted in the diagram, which shows one moving and one stationary boundary plate. The equation for this motion is listed last, which is telling us that the force per unit area, represented by the Greek letter tau, is equal to the viscosity, mu, multiplied by the differential velocity, or local shear velocity, between the stationary and moving plates. We now move on to non-Newtonian fluids. We see that there are a few different categories which are all independent of time for which the force is applied. Focusing our attention on the graph, we note that Newtonian fluids exhibit a linear relationship between shear rate and stress. More simply put, the more force over an area we apply to the fluid, the faster it will flow. For non-Newtonian fluids, however, we note there are 3 cases that do not follow this Newtonian response. In the case of a pseudoplastic or shear-thinning fluid, the apparent viscosity decreases with applied shear force. Examples of this are ketchup, syrup, or certain types of paint. In the case of viscoplastic or Bingham plastics, we see there's a certain minimum force needed to begin the flow, and then the fluid will flow in a Newtonian manner. A common example of this is toothpaste or chocolate. The last case, and one which our demonstration focused on here, is that of dilatants, or shear thickening fluids. In this case, the applied shear increases the apparent viscosity of the fluid, making it more firm or solid-like. The fluid in our demonstration falls under the category of shear thickening fluid, but we now wish to discuss how this process works. The primary model for shear thickening is through the formation of hydroclusters. When the fluid is subjected to a large force over a short period of time, or an impulse, the water may quickly disperse from the area of impact, leaving clumps of particles, in our case cornstarch. These clumps form a semi-rigid solid, momentarily changing the fluid into a semi-solid. This will disperse the impact quickly, and the matter will return to its liquid state shortly after that period of time. So, while non-Newtonian fluids seem like just a curiosity, they also have several practical applications. The first follows from our demonstration, which just serves to show the difference between Newtonian and non-Newtonian fluids. In addition, and more practically, work is being done to incorporate these liquids into traction control. When a tire begins to slip, the centrifugal force can harden the non-Newtonian fluid, transferring more power to the other tires through the car's differential. Additionally, the idea has been proposed to use materials like oobleck for shoes which would be comfortable and form-fitting under gentle walking, but toughen up and prevent joint damage during running or other vigorous activity. The last and perhaps most interesting application of non-Newtonian fluids is the integration into body armor. Liquid armor would allow for greater mobility of the user while still distributing blunt force impacts effectively when struck with sufficient force. This concludes my presentation on non-Newtonian fluids, and listed here are my sources of information and the disclaimer that all my images were borrowed from the public domain so no one decides to sue me. For more information on non-Newtonian fluids, search the above resources as well as the World Wide Web. Thank you for watching, and continue to explore the fun side of non-Newtonian fluids by viewing additional videos on YouTube. Thank you, and have